Okay, can you hear me now?
Yes.
Okay, thanks, Jake.
Yep. Thank you.
All right, thanks, Jess. Okay, so with convection, the physics of convection is really complicated, but we can simplify it down and kind of dumb it down to a really simple model. So we have right here, we have the heat flux, a single variable H, which we call the convection coefficient, and then two temperatures, Ts and T infinity. Right, so Ts, that is the surface temp, and T infinity is the fluid temp far away from the surface, or some large distance away from the surface. Okay, so the interesting thing about convection, at least for me, one of the interesting things about convection is, right, this is just proportional, right? So if you have a convection process where the air is 20 degrees and the pancake griddle is 200 degrees, right? You have a 180 degree temperature difference. If instead of that, you had the air at 20 degrees and the pancake griddle at 110, as long as your convection coefficient is the same, the heat transfer just like got cut in half, I guess. Right, so it's directly proportional to what the difference in temperature is. It's just linear. I mean, we know that it has to have something to do with it, but the fact that it's just linear in temperature is really kind of interesting. And that gives us two different processes, conduction and convection, that are both linear. Right, our conduction, if we go back, right, our conduction in a lot of cases like that is just linear in temperature as well. So we're going to use that, and we'll use that to our advantage, that both conduction and convection, at least in simplified cases, are both kind of basic linear with temperature. If you double the temperature difference, you double the conduction. If you double the temperature difference, you double convection. Just a really useful and handy, like, you know, if you walk away with nothing else from this class, that's useful. Okay, so let's jump back in and talk a little bit more about this process. So we can simplify all of convection, the whole crazy physics, down to H. So really, the trick of convection is predicting H, right? Because if we knew H, it's really easy, right? The temperature of the surface, you can measure that really easily. The temperature of, say, the air or the water or whatever fluid it is, you can measure that super easily. You put a thermometer in it. H is where the complexity is, and where actually, like if you're trying to do a design process, that's where you're trying to figure out, how can we control H? How can we figure out what it might be, what approximately it should be in these conditions? If we made this design change, how would that change H? You're going to be centered most of your thought on what is this thing and how do I control it and how do I figure out what it might be. But if you know H, everything's easy. So H depends on a number of different things. It depends on the the surface geometry. So for example, if our pancake griddle is perfectly smooth, or if it's rough, or if it's flat, or if it's curved, or like a circle, or whatever funny shape it is, all of those things are going to change it. It depends on fluid properties. And this is where things can get really exciting because fluid properties change with temperature. And we already said, right, if I just flip back to here, if fluid properties change with temperature, the temperature down here is different than the temperature here in the middle, is different than the temperature here at the top. So things get exciting. Okay, so it depends on the surface. It depends on fluid properties. Just an example of some of what those would be, like heat capacity, thermal conductivity, whether we have boiling or condensation. Whether how those things change with temperature. So if you have something that, like the fluid is condensing, or it's a liquid and it's boiling as it goes along the surface, that's going to change what H is pretty dramatically, actually. It's going to change on the nature of fluid motion. Right? Whether it's fast or slow or laminar or turbulent, how the fluid is actually moving, right? This is something that makes perfect sense. But one of the cool things about it is, despite all of this, it is only weakly dependent on temperature. Right? It is dependent on temperature. It does change with temperature, but not as much as as these other types of things. Okay, and that's cool because then you can do a set of experiments under some conditions and use that knowledge to translate it to, say, the conditions that you're interested in. So this gives us a way to tackle it not only with equations and with models and stuff, but also experimentally. And we'll get into that. And how do you design experiments with, say you have a process that would be unsafe to do the full-scale experiment because maybe it would blow up or something if you did it wrong, right? You maybe want to do experiments with a different system so that you know what the answer is before you go to the full-scale thing that could blow up if you did it wrong. So how do you make sure you design like good experiments that, you know, your reactor is not going to melt and explode and something like that? How do you do the smaller scale, more safe experiment? How do you translate some of those things? So we'll learn about that as well. Okay, just to give an idea of the range of convection values or convection coefficient values. And again, you don't have to write these down, but you'll have them here and we'll use them. But just to give kind of like a mental map of what this might be. So free convection, that's convection, like if you have something hot, oftentimes, right, you'll get density changes in, say, the air as it heats up, and that air will start to rise, and you can get some like airflow off of a hot thing, right? We've all experienced this and seen this. If you ever like look on a summer day, you know, at the top of a grill, you'll see kind of these funny lines. It's fun. They're called schlieren. which is a fun German word. So you can impress your friends at the next cookout. The lines you see, it's actually from the change in density of the air. But it's essentially, it's the air that's hot rising off your hot grill. So that would be free convection. You don't have a fan blowing. Forced convection is you have some sort of fan, right? I mean, pushing liquid, forcing the liquid movement, or forcing gas movement. Forcing convection. Free convection, one thing to, right, there can be a huge range of values. This is just like an approximate ballpark range for what those might be, but they're going to be small-ish numbers. If you go from a gas to a liquid, you get bigger numbers, right? Liquids are going to be better at cooling because they're higher density, right? So they can more effectively remove heat from a surface. Okay, so how much more? Well, like a lot more, 10 times, 50 times, depending on the liquid, depending on the conditions. But they're a lot better at convection. Forced convection, if you are making something move, right, then obviously you can jump again, but you're jumping by a factor of, depending on the velocities and everything, you're jumping by probably a factor of 10 or 20. So it actually, going from a gas to a liquid, right, matters more than going from a gas that's not blowing to like a fan blowing on something. Like if you switch from a gas to a liquid, that makes a bigger difference. And then the biggest difference, okay, if you can go to something that has a phase change, right, something that's boiling or something that's condensing, that's where you really get big convection coefficients. Does anybody have a Surface that doesn't have a fan, like a Microsoft Surface with them? No? I think some of the ones, so all of our my computer has a fan, right? Because you want to get the heat out of the inside of the computer, and you want to go from, something in this range to something in this range. I think some of the fanless surfaces, instead of doing that, they have like a liquid cooling that you actually have a boiling of the liquid. So you're going from not a free convection to a forced convection, you're going from a free convection to a free convection with a phase change. And that's how you're getting the higher convection coefficients. But then you can do that without moving parts and without fans. It's kind of fun. Okay, so let's solve our problem. All right, so we had our pancake griddle. Let's assume H equals 10. The units on that are watts per meter squared Kelvin. So the units for, right, we have these like two kind of things, one for conduction, one for convection. The units are really similar. Okay, so the units on H, watts per meter squared Kelvin. Okay, the way that I remember, right, the units on conduction, if I can scroll up a second, right, on thermal conductivity are watts per meter Kelvin. So we have a watt per meter Kelvin and a watt per meter squared Kelvin. I remember them and keep them apart because conduction happens through something, meter. Convection happens over an area, meter squared. So that's why the two are really similar. They're both similar types of things, but one is conduction through something, so you get just meter. one is convection over a surface, meter squared. Okay, so just, I don't know, hopefully that helps you remember. Okay, so let's imagine for our pancake griddle, we had, again, figuring this out, maybe it takes experiments, maybe it takes some modeling and prediction, but let's say we figured out that H was 10 watts per meter squared Kelvin. Then Newton's law of cooling says that Q double prime equals H T S minus T infinity. Q double prime equals, this would be 10 watts per meter squared Kelvin times the surface temperature was 200 C. The air temperature far away was 20 C. So that equals 1,800 watts per meter squared. And then if we want to figure out just in the the total cooling rate in just watts, we can figure out that with our area. So the heat rate Q equals A times Q double prime. So Q equals, I don't remember what our dimensions were, 60 by 20. So 0.6 times 0.2 meters squared times 1,800 watts per meter squared. Then Q would be 216 watts. Okay, so in these conditions, the way that you would keep your pancake griddle at a steady 200 degrees Celsius, it's going to need 216 watts of power. So that would be the power draw. Yeah, Liz.
So this would be true for like any griddle of any size. Because we're multiplying size.
This would be.
Yeah, that's what I meant.
Yep. But geometry matters. So if you had a bigger griddle, you're going to have a different H in the same conditions. If you had a smaller griddle, you're going to have a different H. So if the H is the same, yes, but that depends on all of the details. And we'll see, as for now, we won't care. We'll just make up numbers. This is how we're going to deal with convection for the next long time. We'll just say, let's say it's 12. And that's all we're going to think about it. And we'll come back and we'll build some of that complexity in. Yeah, Brennan.
Do the temperature units for H have to match the other temperatures? So like H is in Kelvin, what the temperature is?
So no, because it's a temperature difference. So yes, but because, right, to get from Celsius to Kelvin, you would add 273 to each number, and then you just subtract those off again. So a temperature difference in Celsius and a temperature difference in Kelvin are both equivalent. But because it's a delta, this is delta T. But my general rule is if you're doing things in Celsius, you sometimes can be wrong. If you're doing things in Kelvin, you're almost never wrong. So when in doubt, if you flip things to Kelvin and then do it, and you turned out like you did 2 extra button pushes on your calculator to add 273, okay. So you generally, if you're unsure, I would just do it in absolute temperature. Okay, so that is convection. So conduction, convection. The last one is radiation. So let's do another example. Okay, so a satellite is somewhere in space orbiting the Earth. What's its temperature when the sun's shining? Okay, so it's not touching, it's in space, so it's not touching another solid surface, so there's not conduction happening. It's not touching any fluid because it's in space, so there's no convection happening. So the only thing happening is radiation. Okay, so let's imagine, just for the sake of easy geometry, that's that's not a circle. Okay, let's imagine we have a circle. That's 1 meter. That's our satellite. Okay, if we looked at the surface of our satellite, okay, it's going to be exposed to light from the sun. So there's going to be radiation hitting it. And it's also going to be emitting radiation. So there's going to be radiation hitting it from the sun, which we'll call G. And there's going to be radiation emitted from the surface, which we'll call E. We'll look at E first. Why would it be emitting radiation? Anybody? Because everything is emitting radiation. You are emitting radiation right now, where you sit. You don't see it, but if you had a thermal imaging camera, the reason that works is because that's just taking a picture of the light that you're emitting. So all of you are glowing there while you're sitting in your seats. You're just glowing in a wavelength range that we can't see, which is kind of fun to think about. So the walls are glowing, you're glowing. You are glowing brighter than the walls because you're at a higher temperature. If you got hot enough, then you would start glowing like the sun does, but you'd probably not be cozy before that happened. Okay, so all of you are glowing though. All of you are emitting radiation all the time. Everything at a temperature is emitting radiation. We're surrounded. You can't get away from light. It's not all visible light, obviously, but you can't get away from it. So what does that look like? So that's the E part of it. That's the light that this satellite is emitting all the time. Everything is, because it's at a certain temperature. So E equals emissive power. So it's something in watts. Or I guess this is watts, or you can write a watts per meter squared in emissive heat flux. This is okay. So if you look at if you look at what we call an ideal radiator, there's some things, if you haven't seen radiation before, some of the terminology is going to be maybe a little weird. But if you have an ideal radiator, then we'll call it EB equals sigma A sigma TS to the fourth. And I'll pull this apart a little bit so that we can figure out what that is. Okay, so what is an ideal radiator? So one of the fun parts about physics is that absorption and radiation are linked pretty closely in terms of like physically what's happening. So for light to be absorbed, if you're a little molecule and you're absorbing light, like, you know, a dye in my shirt, if you're a dye molecule, what happens, light comes in and that molecule absorbs that light and goes from the energy state that it's currently at to a higher energy state. Okay. For emission to happen, we start from a higher energy state, we emit light and go to a lower energy state. So it's like the exact reverse. So absorption and emission, in terms of physical mechanism, why they happen, what's physically happening when atoms and molecules, they're really similar and like the opposite of each other. So what would be something that is an ideal absorber? What would that mean? It means it absorbs all of the stuff. What does that look like to your eye? What color is it? It's black. So what would be something that is an ideal emitter? What color would it be? Black. Still black. It's the same thing. So for absorption to happen, that process, if that works really, really well, that thing is black. If absorption works really, really well, emission also works really, really well. So they're linked together. So for you to be an ideal absorber, you're a black thing. If you're an ideal emitter, you're a black thing. So we call that ideal radiator. This is black body radiation. And it really does like physically mean that it's because the thing is black.
What's the worst color?
Shiny things.
So like silver?
So if you have like so you've ever seen a space blanket?
Yeah.
The super thin ones, what color are they?
Right.
They're like foily, right? Why are they that color? Because that limits radiation. So we'll figure that out. And actually, if you look at if you've ever seen a spaceship or a satellite, what color are they typically? Like the lunar lander.
Like the gold foils?
They're like gold foily, shiny things. Why are they shiny? That's space insulation. You don't use, for insulation in space, you don't use like big, thick foam insulation because that actually doesn't work well. You use really thin, papery, shiny stuff. Anyway, wild. We're not going to cover all of that right now. But okay, so for something to be an ideal, perfect emitter, it's going to be what we call a black body. Now, this is a little bit simplified. Like, it's okay, it's not. That's true. And not everything that is a pretty close representation of a black body, as we talk about an emission, is actually black. Like, my shirt is not black. If we were to look at how close is this does this represent a black body? It's probably 95% or better. But that's because the light, right? The light that you guys are all glowing is not visible light that we can all see. It's infrared. So when we're talking about a black body, it's something that perfectly absorbs the light that's hitting it, whether that's infrared light in a lot of cases. So this gets a little bit hairy with terminology because you can have something that's not black at all, that's white, that behaves like a black body because the light that's shining on it, or like the light that it's emitting, is in the infrared where, right? So color right? Don't just use like color as a proxy for, is this a black body? No, it's white. Like, well, it could still be a black body, or really well approximated by that. Okay, so going on too much about that. Okay, so this is black body radiation. A is obviously the area. Sigma is the Boltzmann's constant, which is one of my favorite physical constants for simply this reason. Look at what it is. 5.67 times 10 to the negative 8, 5678. Watts per meter squared Kelvin to the fourth. Okay, so that's Boltzmann's constant. Now, if you look at, I just want to talk briefly, and we're not going to talk more about this, but I think it's useful to see if you've never seen it to help you understand radiation a little bit. We'll talk briefly about black body. Black body radiation. So you would have something like this. This is like watts per meter squared, Kelvin to the fourth per nanometer. Okay, don't worry too much about the units. That's the y-axis is power. And this is wavelength. So it has units of something like nanometers. This is the color. So if you were to look at this, so this would be like UV over there at short wavelengths. Visible and infrared. Okay, if you were to look at the sun, what does the sun look like? It looks pretty much like that. So this would be the sun. So one of the kind of fun things about black body radiation is it has a way bigger importance historically than you would believe. Maybe you'll believe it after I tell you, but than you would expect. So people early on, like the turn of the century, before the turn of the century, in 1862, started looking at like what light does the sun emit, and they saw this kind of thing where it emits mostly in the visible, some in the IR, and some a little bit in the UV, but it's this kind of shape. And then they tried to describe why that happens. And they came up with laws like this, like how can we describe, how can we correlate temperature with emission? They started to figure out that, right, everything emits light. You've figured this out when you've ever roasted marshmallows and like left your marshmallow stick in the fire and it turns red hot. Right, that's all we're talking about. So if you have something that's really hot, it's going to be emitting in the visible spectrum. If you have something that's not as hot, right, this is maybe like your marshmallow fork sitting in the fire, it's going to get what we call red hot, right? This is how we talk about things. And that's going to look like this. It's going to look like that. So this is your okay. Now, you personally are going to look like that. That's you. You're going to emit just a tiny bit of light way in the IR. Why? Because your body is not super warm. So why are these things different? It's because the temperature is different. So as the temperature changes, as the temperature increases, we shift from the IR, we shift on this graph, we shift to the left into the visible. And that's why we talk about something being red hot and something that's hotter being white hot, like the sun. If you look at like stars or anything, you can tell what temperature they are based on what color they are. If they're red, they're cooler. If they're white, they're hotter. If they're blue, they're hottest. Right? So you can look at that and figure out what the temperature is, because where they're emitting light changes based on temperature. So the color changes based on temperature. Also the amount, right? You can see the sun is emitting a lot more light, a lot more power than your marshmallow fork, which is emitting a lot more power than your body, right? And that scales as temperature to the 4th power. So radiation at your body temperature is itsy bitsy teeny weeny. At the sun's temperature, it's huge, right? The sun is emitting so much energy that the Earth, which is like super far away, 186 million miles away, it's still hot for us that far away. And that's because it scales as temperature to the 4th power. It's super sensitive to temperature. So in a lot of cases, we're not going to really worry about radiation because the other types of heat transfer matter more. Conduction, convection. If you're talking about like your body, the amount of energy that you're radiating is small. So we usually don't care about it. We usually don't have to consider it, but it's always there. Just some fun facts. So black body radiation was first described by Gustav Kirchhoff. Have you ever heard of Kirchhoff or a Kirchhoff's law? Where have you heard that? Circuits class, right? Like the current coming in is the same as the current leaving. That's Kirchhoff's law. Same Kirchhoff. Have you ever heard of Robert Bunsen? Where have you heard of him? Bunsen burners. So he's most famous now for a Bunsen burner, but he was one of the ones too that described black body radiation. Has anybody heard of Max Planck? What is he famous for? Planck's constant. He's famous for quantum mechanics. So he won the Nobel Prize for describing why black body radiation looks like that. And it led to quantum mechanics and the whole quantum mechanical revolution at the 1900s. So black body radiation, figuring out why stuff works like this, led to quantum mechanics and led to some of this stuff, which I think is kind of fun. And it's from random, like Kirchhoff's law and Bunsen. Those two also discovered cesium and rubidium. So they were like talking about circuits and black body radiation and finding new elements. When nobody knew anything, there was a lot to discover. Okay, so that's black body radiation. Now for a real object, right? We have a slight tweak. I'll box that because that's what we're going to use a lot. We have a slight tweak to our equation. This is, A is still area. This is still the Boltzmann constant. That's the name. TS, this is the surface temperature. So radiation is something that happens at object surfaces, not inside objects. So it's a surface effect. So we care only about, like, if you want to look at the sun, for example, the key thing is the surface temperature of the sun, not the temperature of the core, right? It's the sun's surface. And then this little epsilon is the emissivity. So the emissivity, epsilon, that's a material property related to how black it is, right? And black meaning, like, not, it doesn't necessarily have to look black, just how well it emits. Where something that is perfectly black across all wavelengths of light, emissivity would be 1. We call that a black body. So emissivity. Now, the flip side of that, right? So absorption and emission always go together, always. So if you're emitting light, you can also be absorbing light. Those two are always linked. So this is for emission, but we have a very similar thing for absorption. So if you have a certain amount of light, this is the that's the total power incident on a body. And this is alpha is the absorptivity. Okay, so epsilon, emissivity, alpha, absorptivity. So for example, okay, you've all experienced the effects of this. So a white shirt outside has a different absorptivity than a black shirt. The sun is the same, but the amount of power that your shirt is, the amount of like thermal energy that your shirt is absorbing is more if it's black than if it's white. That's why the black gets hotter, okay, because it's absorbing more light. So that's true in the visible. That's also true in places like the infrared. So we have to take that into account. Kind of what's the color of the object? What fraction of the light that's hitting it is actually being absorbed? Okay, so you have this kind of complex game. Again, if we go back to our satellite, which is what we started trying to think about. If we go back to our satellite, we had some amount of light coming off of the satellite and some amount of light hitting the satellite. So in space, equals 1367 watts per meter squared. So solar power in space is 1367 watts in every square meter. On Earth, it's about 1,000 when it's sunny out, because you lose some of it in the atmosphere. Like some of it bounces off the atmosphere, some of it is absorbed by the atmosphere. So you're about 1,000 on the surface of the Earth. You're 1367 in space. So that's how much power is coming and hitting the surface of our satellite, not all of that is necessarily being absorbed. Some of it can bounce off, right? Some of it can be reflected. Similarly for, okay, so this is at, the surface of our satellite is going to be at some temperature. We'll call it TS. That's what we're trying to figure out. And that's going to be what's causing emission of light. So we have these two kind of processes. So let's do an energy balance of our satellite. So an energy balance tells us that the energy coming in has to be equal to the energy going out. So the energy going in equals E out. What's coming in is G times alpha, right? How much is coming in times like what fraction of it did we absorb? 10%, 90%, whatever it was. That's going to be equal to the, and I guess we should also have the area. Or we'll call this, let's write it this way to do that explicitly. Times A times alpha. Because we know the per area amount. Obviously those A's cancel out, but just to be clear. That equals how much is being emitted, which is A times epsilon times sigma T S to the fourth. Okay, now as long as we know all of our material properties, right? Epsilon and alpha are both material properties. We know this one, so we know that. We can figure out alpha, epsilon, sigma is just a constant, and then we would solve this for temperature. Okay, so figure it out. Let's assume alpha and epsilon are about the same. And I'll write a note. This is usually actually a pretty good assumption because these are two, like, in terms of physical mechanism, what's physically happening, these are linked. So it's not just a wild thing that, you know, we would expect that these would be similar. They often are similar. We could look it up. This is a measurable property. We could figure it out. But this is a reasonable thing to do, at least for the sake of what we're doing right now. So if that's true, then G over A alpha equals A epsilon sigma TS to the fourth. Then we can divide both sides by A, get rid of those, and we can divide both sides by alpha slash epsilon because those are the same-ish number. So then we would be left with G over A equals sigma TS to the fourth So TS equals, so then we can plug in some numbers. This is 5.67 times 10 to the minus 8. Sorry, I'm doing my algebra wrong. This is equal to 1367 watts per meter squared divided by 5.67 times 10 to the minus 8, and that's watts per meter squared, Kelvin to the fourth, all raised to the 1/4 power to get rid of our fourth power on temperature. Okay, if we figure that out, we get that the surface temperature is equal to 278.6 K, which is like 5.4 degrees C. Okay, so a couple interesting things to note about this. The hardest thing that we'll run into about radiation problems and heat transfer in general, it's some of the equations that are like the simplified equations that we'll use for radiation can lead us astray. Remember, what we're trying to do in radiation problems is do really what we did here. And this is true for a lot of heat transfer problems. Really, like you can, if you think of it like an energy balance, energy in, how much energy is coming in, how much energy is leaving. I think that will give you the best success rather than like, here's the equation I found in my book. Let me just plug in my numbers. Because sometimes those can lead you astray. So how much is coming in, how much is leaving? And I'll show some of the equations that our book gives here in a second. But another cool thing, we just figured out why the Earth is the temperature that it is, pretty much. And how you could, with something like global warming, how that would work. It would work by changing alpha and epsilon. Right? So if you're decreasing how much light you're absorbing as the Earth, you're decreasing alpha, that would get you colder. If you're decreasing how much light is being emitted, that's going to get you warmer. So the relative balance of alpha and epsilon. So for the Earth, that's not exactly true. It's pretty close to true, actually, because the average temperature of the Earth is like 15 Celsius. So it's really close to true. But if you change that balance at all with something like carbon dioxide, then you get into a place where, you either get warmer or cooler. So fundamentally, why global warming happens is because you're changing the relative ratio of alpha and epsilon. You're making one a little bit bigger and not changing the other one. Okay. Okay, so let me just show, and I'll show this because you'll see this a lot in our book. In a lot of circumstances, this is kind of the picture that we'll have for radiation. You'll have two different things exchanging radiation. So let's think of you. Okay, you are emitting light. You're emitting heat. You are also absorbing heat energy. You're absorbing heat energy from the walls of the room, from the floor, from the ceiling, from the other people in the room. So you're emitting heat energy, but you're also absorbing it. So it's usually like a two-way street. It's only very rarely not some sort of like back and forth. So it's often this kind of like two-way thing where you're emitting light, but you're also absorbing light from somewhere else. And like there's this back and forth. So fundamentally, like I said, like we did, it often is something like this, right? So we have, okay, how much are you emitting? Right, it's an energy balance. How much did you emit? How much did you absorb? Right, how much did you absorb? Now, often figuring out G, right? If you're absorbing what something else is emitting, you could basically rewrite this equation here, like the left-hand side, and plug that in for G, if that makes sense. And we'll do this explicitly so that you can see how it works. But if you have a situation like this, okay, so how much heat is that guy emitting? Epsilon t to the fourth, epsilon sigma t to the fourth. Okay, but it's emitting light from, or it's absorbing light from this guy, which is emitting epsilon sigma t to the fourth. So if you want to figure out how much power this one's emitting, epsilon sigma t to the fourth. So you end up getting like similar terms in both cases. So that's how you end up with something like this equation, where you have, so this is the surface, and this is what we call the surroundings. And we'll go through and figure this out in more detail. Forget that part for now. So again, some just kind of general rules of thumb. Things that are shiny have low emissivity and low absorptivity. So things that are like, that you view as shiny, if it's shiny, it's probably alpha and epsilon are probably low numbers. If it's something transparent that you can see through, that doesn't mean that epsilon and sigma are small. Water is pretty much a black body. You can see through it, but in a lot of wavelengths, it's basically acts as a black body. Liquids typically are pretty good approximations of a black body. Gases are not. Gases are usually transparent to radiation. When I say that, that's not totally true. Gases emit light. Everything at a temperature emits light. Gases are just super low density. So the amount of light that they emit or absorb is small. So usually we consider them transparent. So for you sitting in your chair, you're exchanging heat with the walls more than you are with the air in the room, because the total amount of energy that the air in the room is absorbing and emitting is really small. So usually gases, transparent, solids, and liquids are really what we're talking about. Okay, so solids, usually opaque. Sometimes they're semi-transparent. Liquids are typically opaque. Gases are typically transparent, which is, I don't know. I don't know how that makes you feel. Maybe happy. Okay, so let's do the problem that you have in front of you. Okay. So let's pull up that problem, and we'll hopefully be able to see some things about how we can go about solving more complicated things. Right, so we've done, at least briefly, all of heat transfer. So now we can put this together and have things that more than one thing is happening at the same time. We're going to do that fundamentally with our favorite tool from thermodynamics, which is an energy balance, right? Energy cannot be created or destroyed, so we can follow where it goes. That's what we're going to be doing. Okay, so we have a thin metal plate of area A. It's insulated on one side and exposed to the sun on the other side. Solar radiation on the plate is 1,000 watts per meter squared. The plate dissipates heat by convection. So convection to the ambient air at 300 K with a convection heat transfer coefficient of 20 watts per meter squared Kelvin. Okay, so one way that it's gaining heat from the sun. It's losing heat to the air by convection. It's also losing heat by radiation to the surroundings, which may be assumed to be a black body at T sky of 280 degrees. So gases are transparent to radiation unless you have a lot of them, like the whole atmosphere. Then that can act as like a faraway black body that is radiating and absorbing radiation. It's a little weird feeling until you do it a few times and get comfortable with it. Okay, and then the absorptivity of the plate is 0.89. The emissivity is 0.9. Determine the equilibrium temperature of the plate. Okay, so which modes of heat transfer are important? Yeah, just convection and radiation, right? So we're absorbing stuff from the sun and we're radiating heat and we're absorbing stuff from the sky. So we have a lot of radiation stuff going on. We're insulated from the ground, which that is the key word that tells us that no conduction is going on. Okay, so insulated on one side. Draw a scheme of the process. Okay, so I would draw something. We have a plate sitting on the ground. Okay, so that part is insulated. The surface is at some temperature. That's what we're trying to figure out. And then it's emitting light. Okay, so it's emitting light because it's at a temperature. There's convection happening. So let's draw that. So this is the typical convection. We'll draw some arrows in kind of a little fluffy cloud. This equals 20. All convection happens by fluffy cloud. So that's kind of my standard picture of it. And this is 20. What's the temperature of the air? 300. This is T infinity is 300 K. All right. Now the other modes of heat transfer, it's absorbing light from the sun. So we have somewhere up here, the sun. There's light G. We'll call this E. Okay. And then there's also this stuff that's happening with the sky. So the sky is acting, I'll kind of draw it like this. So this is the sky. And we're saying T sky equals 280 Kelvin. And this is emitting light, call that G sky. Okay, so we have a lot of things going on, which is why drawing a picture like this can help us. Okay, what else do we know about our system? We know that for our plate, alpha equals 0.89 and epsilon equals 0.9. And we know the sky is a black body. So this is alpha equals epsilon equals 1. So a black body, both alpha and epsilon, both are 1. Absorptivity and emissivity. Okay, so let's write an energy balance for this whole process. Okay, so the amount of heat coming into our plate is going to be equal to the amount of heat leaving our plate. So E in equals E out. And for me, this is the easiest way for my mind to figure out all the sign convention and stuff, is just to say the in equals out while we're at equilibrium. So where is heat coming in and where is heat leaving? I don't know. I mean, we can kind of say whatever we want as long as we keep our signs right. But how I have it drawn, to me at least, it looks like heat is coming in from the sun, and we also have heat coming in. So we have heat coming in from here, and we also have heat coming in from there, both as radiation. That's how I have it drawn at least. Okay, so that would be, the in is, okay, so how much heat is actually coming into the plate from the sun? It's going to be the amount that's hitting it times how much actually made it in as heat. So G times alpha, like how much struck it times the absorptivity. So G sun times alpha. So that's how much is coming in from the sun. How much is coming in from the sky? It's going to be, again, the same thing. How much is coming in times how much actually got absorbed. So this will be, how much is coming in from the sky? It's epsilon sky sigma T sky to the fourth, right? That's how much the sky is emitting. Yeah, Jared?
Are we taking out the areas where it'll be canceled?
Yeah, I can put in areas. That's a good idea.
I'm just asking if you're doing.
I'll put them in. They will be canceled, but I'll put it in for completeness. That's a good idea. So A times alpha. Okay, so that's the total amount of heat that's coming in. That's going to equal the total amount that's leaving. Okay, so that's how much heat is leaving. Well, it's leaving by two processes. It's leaving by emission, and it's leaving by convection. So let's do the emission part first. It's A epsilon. This is from this is from the sun. This is from the sky. Emitted from the plate, sigma T S to the fourth. Plus, for convection, it's the area times H times, okay, so this is where it can get a little confusing. TS minus T infinity or T air. Okay, and this is okay, so those are our 4 processes. And it doesn't really matter, like perhaps it could be that the equilibrium temperature of our plate is below the temperature of the air, like it's below 300, which is fine because our signs will work out. Like if this guy over here on the right, if this ends up being a negative number or a positive number, that doesn't really matter. The signs will work themselves out. So you don't actually have to know if this is heat that's coming in or if this is heat that's leaving, as long as you track everything the same, like the signs will figure themselves out in the end. Okay, so the last bit, and we'll finish there, would be how would we go about actually figuring out then the equilibrium temperature? And the trick is once we have multiple modes of heat transfer, if radiation is one of them, it stops being really straightforward to figure out. Like we can figure out, okay, so that's going to be a number. That's going to be a number. But this is temperature to the 4th, and this is temperature. So we can't just get a nice, easy analytical solution, which is fine because we can solve it really easily in some computer program and and that's what we'll do next time. We'll plug this in Excel and we'll use Excel to figure out, okay, how do we actually solve the energy balance and vary the surface temperature and basically do like a guess and check method. So that's what we'll do next time using this energy balance. So keep this paper and join us next time for that. All right, well, hope you guys all have a good Thursday. Thanks for joining, and I'll see you on Tuesday.